A mountain of rock is waiting in deep space. For all of human history, we have watched objects like this move exactly where gravity demanded. We learned to discover them. We learned to predict them. But we had never changed the path of even one. Then a spacecraft left Earth with a very different mission. Its destination was a tiny moonlet named Dimorphos, circling a larger asteroid called Didymos. From Earth, it appeared as little more than a distant point of light. It posed no danger to our planet. That was exactly why it had been chosen. If humanity was ever going to test whether an asteroid could be pushed onto a different path, this was the safest place to try. For decades, planetary defense meant observation. Astronomers searched the sky night after night, cataloging near-Earth objects and calculating their future positions. Every new discovery made predictions more accurate, but prediction alone could never answer the question that mattered most. If a dangerous asteroid were ever found with enough warning, could anyone actually move it? Until now, no mission had attempted to find out. The idea sounded almost unreasonable. For decades, spacecraft had explored the solar system by observing it. They landed. They orbited. They collected samples. This mission would do something none of them had attempted. It would deliberately strike a natural celestial body. Not to destroy it, not to study the impact alone, but to test whether its orbit could be changed. That objective transformed planetary defense itself. Instead of asking only how accurately humanity could measure an asteroid's motion, engineers began asking whether that motion could become an engineering problem. The asteroid changed meaning before a single bolt was tightened on the spacecraft. Dimorphos was no longer simply another object following gravity's instructions through space. It had become the first target in history selected for an intentional planetary defense experiment. Official mission documents described exactly that purpose. Not a flyby, not a landing, not a sample return, a kinetic impact test. The plan was startlingly direct. Launch a spacecraft from Earth, guided across millions of kilometers of space. Find a moonlet barely distinguishable from the larger asteroid it orbited. Then deliberately collide with it at extraordinary speed. No one yet knew whether such an impact would accomplish anything meaningful. The mission itself did not promise success. It promised only an experiment. The question that had existed only in computer models was now riding inside real hardware. As the launch vehicle stood waiting on the pad, the entire investigation narrowed to one visible object. Not the asteroid. The spacecraft. Everything that followed depended on whether this machine could accomplish something humanity had never attempted before. The launch would answer only the first question. Could the journey even begin? A Falcon 9 rocket lifted away from Earth in November of 2021, carrying a spacecraft that weighed just 570 kilograms. Against the scale of space, it seemed almost insignificant. Ahead lay millions of kilometers of empty darkness. Somewhere within that distance, two asteroids circled each other. One was large enough to be tracked with relative confidence. The other was a tiny moonlet. Dimorphos, the object that actually mattered. Reaching the asteroid system would not be enough. The mission depended on striking the smaller body, not its larger companion. Missing by even a small distance would leave the experiment unfinished. The farther the spacecraft traveled, the less useful direct human control became. Signals needed time to cross the distance between Earth and the spacecraft. During the final approach, there would be no opportunity for mission controllers to watch live images and steer the vehicle around the last obstacles. The spacecraft would have to finish the mission alone. Its forward camera became more than a scientific instrument. It became its eyes. For months, the asteroid system remained little more than a destination calculated by mathematics. Gradually, faint points of light began separating inside the camera's view. The larger asteroid appeared first. Its smaller companion remained difficult to distinguish. At this stage, reaching the neighborhood still did not mean reaching the target. The investigation entered a different phase. Distance stopped being the primary challenge. Precision replaced it. The spacecraft carried autonomous navigation software designed for exactly this moment. Instead of waiting for instructions from Earth, it continuously examined its own camera images, identified the correct target, and calculated tiny course corrections by itself. Every correction committed the mission more completely. There would be no pilot taking over during the final seconds. The spacecraft had become its own navigator. Minute by minute, the images changed. What had once been a faint point slowly gained shape. Then separation. Then depth. The larger asteroid drifted across the frame, while the smaller moonlet revealed itself beside it. For the first time, Dimorphos no longer existed only as a distant astronomical measurement. It had become a visible destination. Yet even now, success remained uncertain. The spacecraft was closing at nearly 6.5 kilometers every second. At that speed, even a tiny navigation error would carry it past the moonlet forever. The autonomous system continued making its own decisions. Each new image refined the spacecraft's understanding of where Dimorphos would be moments later. Not where it had been, where it was going. Mission telemetry showed the guidance system locking onto the moonlet during the final approach. From that point forward, every maneuver served one purpose: keep Dimorphos at the center of the camera. Nothing about the scene looked dramatic. There were no explosions, no engine burns lighting the darkness. Only a silent spacecraft making countless invisible calculations while a tiny world slowly expanded ahead. The investigation had changed again. The question was no longer whether humanity could send a spacecraft across interplanetary space. That had already been answered. A more difficult question remained. Could a machine built on Earth actually hit something this small, moving through space with nothing left to correct its aim except itself? The answer was only seconds away. The camera never looked away. Frame after frame arrived from the spacecraft as Dimorphos grew larger with astonishing speed. The tiny point that had taken months to reach was now transforming with every passing second. The surface was no longer an abstract destination. Individual shadows appeared, then jagged ridges, then enormous boulders scattered across the moonlet without any obvious pattern. There were no smooth plains waiting below. The landscape was a chaotic field of broken rock held together only by the asteroid's weak gravity. The closer the spacecraft came, the less familiar the surface looked. It resembled a mountain collapsed into countless sharp blocks, suspended in the vacuum of space. The camera continued transmitting. Each image carried more detail than the last. The closing speed never slowed. Every second erased several kilometers from the remaining distance. Nothing in the mission profile called for evasive action. The spacecraft had reached the only moment it had been built to achieve. Inside Mission Control, engineers watched the incoming images, knowing they represented the last moments of the spacecraft's existence. No command could save it. No maneuver was intended to. The final approach had become completely irreversible. One enormous boulder filled part of the frame. Then another. The surface no longer resembled an asteroid seen through a telescope. It looked close enough to touch. The cadence of the images accelerated as the distance collapsed. Every transmission showed less empty space and more fractured stone. The investigation that had begun with orbital calculations had narrowed into something almost painfully simple. Would the images stop where they were supposed to stop? One frame arrived, the next never came. At 23:14 Coordinated Universal Time, on September 26, 2022, the spacecraft struck Dimorphos at roughly 6.6 kilometers every second. The loss of signal was exactly what the mission expected. Independent telemetry and the final image timestamps converged on the same conclusion. The spacecraft had not flown past the target. It had not clipped its edge. It had impacted precisely where it was intended to. The engineering objective was complete. The spacecraft no longer existed. Its aluminum structure had been destroyed on contact, transferring its enormous kinetic energy directly into the asteroid's surface. For the first time in history, a human-built machine had intentionally collided with a natural celestial body as part of a planetary defense experiment. It felt like the investigation had reached its answer. After all, the mission had succeeded in hitting its target. But nothing in the final image proved the one thing the experiment had actually been designed to measure. The camera could no longer see. The spacecraft could no longer transmit. No photograph could reveal whether Dimorphos was still following exactly the same orbit around its larger companion. The asteroid remained. The evidence had vanished with the spacecraft. Only one witness was left: Dimorphos itself. And it would take time before it revealed whether anything had truly changed. The spacecraft was gone. Nothing more could come from the point of impact. If the mission had changed anything, the evidence would have to come from an object still silently circling another asteroid more than 11 million kilometers from Earth. Dimorphos continued its orbit. From that distance, no telescope could watch it move directly around Didymos. The separation between the two bodies was simply too small. Instead, astronomers watched something far more subtle: the brightness of the system. Each time the smaller moonlet passed in front of or behind the larger asteroid, the combined light reaching Earth dipped slightly. The pattern repeated. Again. And again. Long before the collision, those repeating changes had established a precise orbital period. One complete circuit took about 11 hours and 55 minutes. Now the same observatories began measuring the pattern again. At first, nothing dramatic appeared. The asteroid did not suddenly veer away into space. There was no visible scar large enough to detect from Earth. Only another sequence of faint changes in brightness. The investigation had become an exercise in patience. Every completed orbit added another measurement. Every measurement could either strengthen the claim that the impact had mattered or quietly erase months of engineering ambition. The simplest expectation remained difficult to dismiss. A spacecraft weighing only 570 kilograms had struck an asteroid vastly more massive than itself. Perhaps it had shattered against the surface. Perhaps it had left nothing more than a crater. Perhaps the orbit had remained almost exactly the same. One observing team noticed something unexpected. The brightness pattern was returning earlier than predicted. Not by seconds, by minutes. One measurement alone could not settle the question. Instrument errors happen. Weather interferes. Small uncertainties accumulate. The investigation continued. Observatories in different parts of the world repeated the same calculations using independent observations. Night after night, the result refused to disappear. The dips in brightness kept arriving sooner than they had before the collision. Another dataset agreed. Then another. The numbers converged. The orbit had changed. Only after repeated observations pointed to the same conclusion did the agencies behind the mission announce the result. Dimorphos was no longer completing its orbit in 11 hours and 55 minutes. It now circled Didymos in approximately 11 hours and 23 minutes. A reduction of 32 minutes. Far beyond the minimum success threshold the mission had been designed to achieve. The investigation changed immediately. Until this moment, the collision had been only an engineering accomplishment. Now it became experimental evidence. Independent observatories, using different instruments and different measurements, had arrived at the same conclusion. The spacecraft had not merely struck an asteroid. It had permanently altered the motion of a natural celestial body. Dimorphos returned once again. Physically, it looked exactly as distant as before. A tiny point of light against the darkness. But it no longer represented an untouched gravitational system. Every orbit it completed now carried measurable proof that its path had been rewritten. The destroyed spacecraft had disappeared forever. The evidence had not. It continued circling through space every 11 hours and 23 minutes. One question still remained. How could such a small spacecraft produce a change so much larger than intuition seemed to allow? Another spacecraft survived the collision. It had not been built to strike the asteroid. Its job was to watch. As it swept past the impact site from a safe distance, its cameras turned back toward Dimorphos. What they recorded looked nothing like a simple crater. A brilliant cloud of debris was expanding away from the asteroid. Long, bright rays stretched into space, carrying shattered rock and dust far beyond the point of impact. The spacecraft that had delivered the collision was gone, but the asteroid itself had begun throwing millions of kilograms of its own material into space. At first glance, the images looked like the aftermath of destruction. But they contained the missing piece of the investigation. The original assumption had seemed perfectly reasonable. A spacecraft weighing only 570 kilograms could transfer only its own momentum, hit the asteroid hard enough, and it should receive a corresponding push. Nothing more. Researchers began comparing two realities. The first existed before the impact. Engineering models predicted how much the orbit should change if the spacecraft's momentum alone did the work. The second came from the telescopes. They had already measured an orbital period shortened by 32 minutes. The two answers refused to match. The asteroid had moved more than the simplest calculations allowed. At first, that difference invited doubt. Perhaps one of the measurements was wrong. Perhaps the impact geometry had introduced a small error. Perhaps the engineering models had overlooked something insignificant. But the discrepancy remained. It was too consistent to dismiss. The explanation was waiting inside the debris cloud photographed after the collision. Every fragment blasted away from Dimorphos carried momentum with it. As rock and dust streamed outward in one direction, the remaining asteroid experienced an equal recoil in the opposite direction. The collision had not ended when the spacecraft disappeared. It had continued through the asteroid itself. Instead of behaving like a solid target absorbing a blow, Dimorphos had become part of the propulsion system. The impact excavated enormous amounts of loose material, and that escaping material acted like the exhaust from a rocket. Not an engine built by humans. A natural recoil created by the asteroid's own shattered surface. The additional push was substantial. Post-impact analyses showed that the escaping debris amplified the deflection beyond what the spacecraft's direct momentum could have produced alone. The asteroid had helped change its own orbit. The collision could now be reconstructed as one continuous physical event. A spacecraft arrived at extraordinary speed. Its kinetic energy struck a field of jagged boulders. The surface erupted outward. Millions of kilograms of rock accelerated into space. The remaining body recoiled. Days later, telescopes measured the new orbit that recoil had created. Dimorphos returned once more. It was still the same small moonlet circling Didymos, but it no longer represented only the first successful collision. It had become the first natural laboratory showing that an asteroid's response can matter more than the impact itself. The investigation had answered how the orbit changed. One final question remained. If this experiment succeeded under carefully chosen conditions, how much of Earth's future planetary defense had actually been proven? The collision was over. The measurements were complete. For the first time in history, a natural celestial body had been placed into a different orbit by human action. It would have been easy to stop the investigation there. But the agencies responsible for the mission did not describe it as the solution to planetary defense. They described it as the beginning. That distinction matters. Dimorphos had been selected because it offered an ideal test. It posed no danger to Earth. Scientists understood its orbit well enough to measure even small changes after impact. Most importantly, the mission had years to prepare. A real planetary emergency may offer none of those advantages. A dangerous asteroid could be larger. Its internal structure could be completely different. It might rotate rapidly, shedding material in unexpected ways. Or it might be discovered far too late for a mission like this to reach it in time. The successful experiment did not erase those uncertainties. It revealed them more clearly. The lesson was no longer simply how to hit an asteroid. It was how much depended on understanding the asteroid before impact ever occurred. The amount of warning, its composition, its size, its internal structure, its response to collision. Every future planetary defense mission would depend on those unknowns. That is why the investigation did not end when the orbit changed. The investigation is already continuing. The European Space Agency's Hera spacecraft is now on its final approach to the Didymos system. Its purpose is not to repeat the collision. Instead, it will examine what the impact left behind. How large is the crater? How was the asteroid's interior arranged beneath its blanket of broken boulders? How much material actually escaped into space? Those answers will allow researchers to compare what they predicted with what nature actually did. The first experiment changed an orbit. The next mission will explain why that particular asteroid responded the way it did. Planetary defense has entered a different phase. For generations, humanity's relationship with asteroids consisted of observation. Find them. Track them. Calculate their future paths. The DART mission added a new capability. Intervention. Only one. Under one set of conditions. Verified by one experiment. Nothing more. Nothing less. Far from Earth, Dimorphos still circles Didymos. From a distance, nothing about the system appears extraordinary. No permanent plume surrounds the asteroid. No beacon marks the collision site. It is still only a small moonlet orbiting a larger companion in the silence of space. Yet every completed orbit tells a different story than it did before September 2022. Before the impact, the journey around Didymos took nearly 12 hours. Now it takes 32 minutes less. The spacecraft that caused that change no longer exists. Its final image ended at the moment of impact. But the evidence survived. It remains written into the orbit of a distant asteroid, repeating over and over again. measurable by telescopes across Earth. The first spacecraft was destroyed. The orbit was not. It continues today on the shorter path, independently confirmed after the collision. That altered orbit remains the first documented evidence that humanity has intentionally changed the motion of a natural object in space.